Hello class, in today's lesson we are going to talk about the merge sort algorithm. This is one of the fastest sorting algorithms out there. We can write it recursively, so there's a great opportunity for us to learn this new sorting algorithm, and it is one of the sorting algorithms that you need to know on the AP exam, along with the insertion sort and selection sort. I will link the videos down below, and of course the Repl.it and the notes down below as well. Let's take a look at merge sort and how it works. So let's imagine that we have this unorganized data here. These purple columns are unorganized data. Now, if we recall from our binary search algorithm, a lot of times a problem can be made much simpler when we divide in half, when we divide and conquer. So the merge sort algorithm takes that to the next level. We keep dividing our data in half. So let's take a look at this. So what if I have 8 items here that are completely out of order? It's going to be a lot easier if I just order 2 sets of 4. So let's do that. Let's move these, let's separate these. So I have 2 sets of 4 now. We'll keep this on the same level kind of. Okay, so I have 2 sets of 4, and I need to organize these 2 sets of 4 into ascending height. Well, if 4 is easier than 8, 2 must be easier than 4. So I think it's time that we split it again. So we're going to split it again, and now I'm going to change the levels here, because we're going to need a little bit more vertical space. So if we split them into groups of 2, this is, again, much easier to order groups of 2 than it was groups of 4. You know what? We can order groups of 1 much easier than we can order groups of 2. So let's split it even more. So now, instead of 8 groups of, or 1 group of 8, we now have 8 groups of 1. Well, each one of these 1 groups is in its own order. How nice. Well, what we can do then is, all we have to do is recombine them. Since they're already in order, we just have to recombine them in order, and this is where the magic of merge sort comes in. The merging is where the real sorting happens. We split it apart into all these constituent pieces, and now we sort. So we're going to sort back to our sets of 2 first. So I take my first pair of 2 that I had, and I compare the height of each one. So I compare this one to this one. And I see that my second one on the right-hand side here is shorter. So when I merge them together, I'm going to put this one, the shorter one, in front. Fantastic. And we do that same thing all the way across, comparing each pair and seeing, putting them back in order. Again, we'll put these in order and these 2 in order. Fantastic. Easy. Now we have 4 sets of 2 ordered lists. Great. Now we need to go back to 4. So what we do now is we think of these as their own little arrays, and we're going to compare the first item in each array to the first item in the next array. And we're going to compare them. Well, the first one on the left is smaller than the first one on the right, so that's the first one we're going to move up. And this is where things get a little different. So I'm going to move this one up, and then I'm going to compare the next one in order on the left-hand side here to the first one over here. Well, we see that it's still smaller than this one, so I'm going to put this one up. So this one becomes, I'll move that down so we have a little more vertical space. So that becomes those 2. Now that I have nothing left on the left-hand side, I simply move each one from the right up and into my new set of 4, and I now have a nice ordered set of 4. Let's move this back down here because we're going to need this space later. Okay, let's do the same thing over here. We're going to compare the first items in each of these 2 arrays. We compare them. We see that this little short one over on the left is the smallest one first, so that goes up. Then we compare the next ones. Well, this one, this big tall one on the left is no longer the shortest one. Now the shortest one is over on the right here, so this one is the one that's going to get moved up. Now we compare the last two items in each of these arrays. We see that the one on the right is still the shortest, so that one gets moved up. And then finally, there's nothing left except for this one over on the left, so that gets moved into the set, and they all get joined together. So we have a nice ordered set here. Now we're going to continue that process. Again, that same algorithm is what we're going to do for the last set. So we'll join them together in the middle here. So we're going to compare the first item here to the first item here. And we see that the one on the right is the smallest, so that's the first one that gets moved in. Then we move one over. If we don't move both of them over, we're only going to move this one over. We compare these two items. We see that the one on the right is still the smallest, so that gets moved over. Now we compare these two. Well, we see that the one on the left is now the smallest, so that one gets moved in. And we move one over on the left, and we compare. This one's a little close, but I think the one on the left is still the smallest. So that one gets moved in. Let's double check. Yeah, that's definitely the smallest. We compare again. We move over on the left. The one on the right is smaller. We now compare one more time to the one at the end of the right. The left side is smaller. We move one more over. The last two items, we see that the one on the left is the smallest. That gets moved over. And finally, nothing left to compare to, so we simply move in the last item from the other set. And that is how we order in the merge sort. We split the list apart into its constituent parts and then reorder those constituent parts into the ordered set. So in the merge sort, we split the data into its parts and merge the parts back together in order. Now, you may be thinking to yourself, Mr. Webster, there's no way that this is faster than insertion sort. But it is. Because if you think about how something would move in merge sort and how many comparisons we would have to do of, say, moving this one little piece all the way to the other side. In something like insertion sort or selection sort, we have to compare that against every single item in the set, right? Which means that we're going to have a large number of comparisons. And it has to move all the way across, right? It has to compare against everything in that array. But in merge sort, because of the way that we split things apart, remember how binary was only log n? Because we split things apart, we have the number of comparisons that this little guy would have to do in order to migrate all the way over to the other side. He doesn't have to compare against the entire list. He only has to first compare against the first one of that first split, and then the first one of that other split, and the first one of the other split, which is log n as many times as he had to if he was in, say, insertion sort. So merge sort is O of n log n. Because we still have to move those items n times, but we only have to do log n number of comparisons. And O of n log n, even though it's a messier looking value than n squared, which we remember our insertion sort and selection sorts were in worst case, O of n log n is much, much faster, right? If our n is, let's say, a million or so, log n is going to be a much smaller number in just a few hundred or so. So much, much smaller number, much easier to deal with. Merge sort is a great, great algorithm. Okay, let's take a look at it in code. And you're thinking to yourself, this is going to be complex. And yes, it is, because that algorithm is complex. There's two methods that we need to look at. And here's what this looks like in code. Of course, this Repl.it is linked down below, so you can take a look at this code and play along with it. There is more code up above with an implementation and a preset array for you that's unsorted, and you can sort it and see how this works. So here's what we do. We first do our split of the data, right? So split the data. P-L-I-T, split the data. Right? And once we're into each of its parts, so once we have gotten down to the smallest unit, then we begin our next set. So this will return, even though this is a void method, the return basically ends the method. So the return will end the method and kick it back up, going, oh, you've reached the end of the line, you're down to just one piece. So this is our smallest unit. Otherwise, keep splitting in half. That's all this does. Keep splitting in half. So this says keep splitting in half. Get all the way down. Keep splitting it. And once you've split it and you've got all the way down and it returns one, or it returns a blank, a void, then finally merge in order. So these two, of course, right here, this is recursive, right? Recursive. So this is a recursive call. Merge is not recursive. Okay, let's go through merge. And it looks scary, but once we look at it a little bit more closely, merge is not too bad. Okay, so in merge, here we go. First thing we do is we create a temporary array. So remember how we were regrouping things back into those smaller sets? We're going to create a temporary array to hold on to. So this is our holding pen, right? For our new stuff. We're going to copy that into our current array soon. So we need to set up some variables. We need a first variable and a second variable. So the first variable is going to be the beginning of where we're going to merge from. The second variable is going to be the second half. So we've got those two split parts. We're going to compare those two split parts, which is from the middle of our searching area to the end. So we're going to take two sets. We've got a beginning and an end. We've split it in half to look at the two parts of this. An I, which is just going to be our iterator to move through temp, and a mid, which at the moment is going to equal second. So it's going to be our middle point. We need to hold on to that throughout the algorithm, but second will move. Okay, so here we are. While our first is less than mid and our second is less than end. So this means that we're moving, we're moving from the beginning of each of those search sets through their respective sections of the array. So while we're still moving through, we haven't hit the end of that section of the array. We're going to check and see. This is our comparison between the two elements. So let's see here. This is moving through the ordered sets. Moving through the ordered sets. And this is comparing them, right? So if the array at the first ordered set is less than our element at the second ordered set, then what are we going to do? Well, we're going to add to our temporary array the item at our first array. So this merges the smallest item to temp. So we've taken it to a temporary place where we're going to store the smallest item. So we're finding the smallest item one at a time, moving through. And notice here, this is really important, first plus plus and second plus plus. If we find it in the first location, we're going to increment in our first location and compare that next item to the same item we were comparing before to second. So we keep moving in whichever one. If one of them in the entire set is smaller than the other one, we move all the way through that set before we get to the next one. So this compares each of the items. Now, what if there's stuff left over? What if, like I said, one of them is completely smaller than the other set? What if the first set is completely smaller than the second set? Well, then we'd have that second set just sitting there all by itself. So that's what these two while loops do. So these two while loops clear any leftover data. So if there's something less than left in first, so first we've gone through and we've compared those items first and second, first and second, first and second, and there's something less left in first, meaning that the index that we've been searching is less than that middle value we said was the end of first. What we're going to do is, while that first is less than our mid value, we're going to increment up in first and add that to the end, to the back of our temporary array to fill those things up. Likewise, if we didn't get to the end of second, then we're going to fill in second. Now, think about this. I have both of these written here, and I don't have an if statement. I don't need an if statement or any kind of other control statement here because, by definition, the way that our first while loop is written, we're going to have to get to the end of one of the arrays, or one of those subsection of arrays. I'm going to have to get to either first equaling mid or second equaling end. So only one of these two while loops will run. Only one will run. Only one or zero will run. And finally, what we do here is we copy our temp array that we built to the array. And then we repeat this for the next set of merges. So because even though merge isn't recursive, because of the way that sort is written, merge gets called many, many times at each call of sort. So merge may be called about as many times as we call sort, right? So even though it's not recursive, it still gets called many, many times, just like sort gets called. So this is the two methods that you need, sort and merge, in order to do the merge sort. And that is the basics. Although it's a little messy to begin with and it takes a moment to wrap your head around, I definitely recommend taking some time to go through this, reading the code, and dissecting it a little bit. Again, I have lots of resources linked for you down below. Thank you for watching all of these videos. That is the end of APCSA Unit 10. That's everything that you need to know for the AP exam. But of course, there's more to come. I'll see you in the next one.